All right, we're back to talking about Raoult's law. Raoult's law says that the vapor pressure of some substance A over a solution is going to be equal to the mole fraction of A in that solution multiplied by the pressure of A when it's a pure liquid, the vapor pressure of the pure liquid. If you have a solution where you have a solute that's also volatile, that's also going to have its own vapor pressure, an example might be something like water and ethanol. Both of these are somewhat volatile liquids and will have their own vapor pressures. We can use Raoult's law for each one of them individually. We can say that whichever one is present in greater amount is going to be the solvent, and the vapor pressure of the solvent is going to be equal to the mole fraction of the solvent times the vapor pressure when it's pure. And we can do the exact same thing for the one that's present in smaller amount, which we would call the solute. If they're 50-50, I guess you could take your pick which one you want to call the solute and the solvent. Doesn't really matter. So we would say in this case that the total pressure over solution is going to be the sum of the partial pressures of the solute and the solvent, and that's going to be equal to the mole fraction of the solute times the vapor pressure of the pure solute, and add to that the mole fraction of the solvent times the vapor pressure of the pure solvent. We'll do a problem in a minute where we use this exact idea. Okay, I'm going to just skip that and we're going to go right to this situation. Raoult's law, first of all, only works if we have solutions that behave ideally. And so the ideally basically just means that they obey Raoult's law. So it's sort of maybe a circular definition. But typically Raoult's law works best when the solute and the solvent have very similar types of intermolecular forces. An example would be benzene and methylbenzene. They're both pretty much nonpolar liquids and have very similar kinds of intermolecular forces. Also, if they're very similar in size and shape, that makes them behave more ideally as well. So we're going to use an example here. We're going to look at a situation of an ideal solution, which is benzene and methylbenzene, and we're saying the vapor pressure of each of those when they are pure are 12.85 kilopascals for benzene, 3.85 kilopascals for methylbenzene. So we could say that P0, let's just say B for benzene, is 12.85 kPa. The P0 for methylbenzene, 3.85 kilopascals. What is the total vapor pressure over a solution containing 2 moles of benzene and 3 moles of methylbenzene? Well, we could say then the mole fraction for benzene is moles of benzene over total moles, which is the moles of benzene is 2, and the total is 2.00 plus 3.00. And that's 2 over 5, which is 0.4. And the mole fraction of methylbenzene is 3 over 5, which is 0.600. So therefore, our pressure total is going to be the pressure of the benzene, which is X benzene times P0 benzene, plus the pressure of the methylbenzene, which is 0.4, no units on mole fraction, times 12.85 kilopascals, plus 0.6, 3.85 kilopascals. There. And that if you multiply that together is 7.45 kPa. Perfect. Some homework questions here, which are very similar, which you guys can do on your own. Second colligative property we're going to be looking at is boiling point elevation. And so boiling point elevation is basically the phenomenon that if you have a solution, if you have something dissolved in a liquid, the boiling point of that liquid will increase the more material you have in there. The equation which governs boiling point elevation is shown here in the blue box. The change in boiling temperature, change in boiling point, which that's equal to the molality of the solution, which means the number of dissolved particles, remember, per kilogram of solvent, so the number of moles per kilogram of solvent, multiplied by the Van 't Hoff factor for the solute. Remember, the Van 't Hoff factor is just 1 if you have a solute that doesn't dissociate. And those are multiplied by Kb, which is the molal boiling point elevation constant. And that is a property of the solvent itself. So here's a good question. Application. Often if you're boiling something like pasta, the recommendation is to add salt to the water. And you'll hear all sorts of reasons for why people do this. Does it help the water boil faster? In fact, no. By dissolving salt in the water, what you're doing is you're increasing the boiling temperature by a little bit. So it actually doesn't speed up the boiling. It actually, if anything, makes it take longer to boil. Some people will say that salt is added to the water to make it boil at a higher temperature and cooks your food faster. That's also really not that true, because the amount of salt that's normally added to water has almost a negligible effect. It does raise the boiling temperature, but only by a very, very slight amount. So the question is, if you're boiling pasta, why would you add salt? And really the answer is because it makes the pasta taste better. All right. Another application, I guess, is when you're making maple syrup. One thing, well, being the way you do this is you collect sap from maple trees and then you boil it. And what happens is, as the water boils out of the solution, the concentration of sugar is increasing. That means the boiling temperature is also increasing. And what you can do is, as you're boiling it, you stick a thermometer in, and based on the boiling point, you can tell what the concentration of sugar is going to be in the solution. So basically you boil it until the boiling temperature reaches a very specific value, and then you know it's done. And the same thing is used when you're making candy. You buy these things called candy thermometers, which give you the boiling point of the liquid. Freezing point depression is very similar to boiling point elevation. It's got almost the exact same equation. The change in freezing point is equal to the Van 't Hoff factor times the molal freezing point depression constant. Again, a property of the solvent. It doesn't matter what the solute is. And that's multiplied by the molality of the solution as well. And so this is a lowering of the freezing point. This has all kinds of applications. A major one is when we salt the roads. And we do this because the salt can form a solution with water from precipitation, from snow and ice, and it lowers the freezing point. And so concentrated salt water has a freezing point of around -12 degrees Celsius. So as long as the temperature is somewhere between 0 and -12, salting the roads will keep the water on the roads as a liquid, as opposed to a solid, so it's not as slippery, not as icy. You can see the same thing with certain species of fish and amphibians that live particularly in environments that can get very cold. They have proteins and other substances in their blood which act as a solute that lowers the freezing temperature of their blood and inside their cells as well, and it prevents freezing. Okay, so here we're going to have a single example which is going to cover off both of these two concepts because they're so similar. And they say if you add 1.5 kilogram of ethylene glycol antifreeze to 4,550 grams of water in your car's radiator, what are the boiling points and freezing points of that new solution? So the Of course, the equation that we're going to be wanting to use here is going to be equal to, it's going to be temperature, change in temperature freezing is going to be I KFM, and the change in boiling temperature is going to be I KB M as well, which is molality. So I guess a great place to start, first of all, is to look at the Van't Hoff factor I. What is it going to be for the solute? The solute's ethylene glycol. It is an organic molecule. It's all held together by covalent bonds. There's no ionic bonding here. There's no metals involved. So the Van't Hoff factor is going to be equal to 1. Nothing's going to dissociate here, which simplifies a little bit. These equations up top, the i's sort of drop out because they're just equal to 1. The next thing we need is the molality of the solution. Remember, the molality is equal to the moles of solute over the number of kilograms of solvent. And the solvent here is going to be the water, and the solute is going to be our ethylene glycol because it's present in lower amount. So what we can do is then calculate the molality, and the molality is going to be moles of the ethylene glycol. Let's call that Eg over kg of the water. So the moles of the ethylene glycol is going to be mass over molar mass. And the mass is given to us in kilograms, which we can turn into grams, 1500 grams, divided by the molar mass of ethylene glycol, which is 62.07 grams per mole. And that equals 24.17 moles. So our molality of the solution is 24.17 moles divided by the number of kilograms of water, which is 4.550 kg. And that gives us a molality of 5.311. Molal is the sort of units we can say. It's moles per kilogram of solvent. Okay, great. So we'll start off maybe with boiling point. We could say delta TB, change in boiling point, is I, which is 1, times KB, which is given, times the molality, units of molality cancel. We're going to get a value in degrees Celsius, and that equals 2.72 degrees C. So the old boiling point was 100 degrees Celsius. The new boiling point is 2.72 degrees Celsius, higher than that. So the actual boiling temperature of that solution is going to be 102.72 degrees Celsius. Which really, if you think about it, we've added a huge amount of solute here to water. And it only changed the boiling temperature. It's less than 3 degrees Celsius. So you imagine that little sprinkle of salt that you'd put in water before you boil pasta. It has an extremely small impact. Okay, we can do the same thing. I think we can squeeze this in here on the bottom. Our delta TF is equal to, again, 1 times the KF for water, which is 1.86 degrees C per molal, times same molality, 5.311. And this gives us a little bit larger of a value, 9.88 degrees Celsius. And so our new freezing temperature, usually it's 0 degrees Celsius. So if this depresses it by 9.88 degrees Celsius, our new freezing temperature is going to be negative 9.88 degrees Celsius, which means it would function as antifreeze down to a certain point at least. The last colligative property we're going to look at is osmotic pressure. So osmosis is a process where you have a solvent move through a membrane. The membranes, we call them semi-permeable, meaning they let some things through but not everything through. The idea of the semi-permeable membrane is that it'll let the solvent through, but it will not let solute pass through them. Our cell membranes operate like semi-permeable membranes as well, so that's an important thing in biology. Basically what wants to happen is the solvent will pass through in an attempt to equalize the concentration of solute on both sides of the membrane. So in the case you see in the picture below, the green things are solute particles. They can't move through the membrane, but the water molecules can. They're going to want to go from the right side, where there's a low concentration of solute, or really no solute, to the left side, and they'll continue to move over to the left side until the concentration is the exact same on both. So you can see this quite readily. If you take, for example, red blood cells, they are, little biconcave discs is the shape, little kind of almost donut shapes, surrounded by a cell membrane that is semi-permeable, that water can travel through to enter the cell, or it can travel out and exit the cell. If you take red blood cells, because they do have some solute inside the cell, and you put them in pure water, this would be a solution we would say is hypotonic, pure water. What would happen is that water will want to pass from the outside of the cell, where the solute concentration is low or zero, to the inside of the cell in order to dilute the inside in an attempt to balance the inside and outside pressures. So what's going to happen is the cells are going to absorb water, they're going to increase in size, and some of them might actually rupture. The opposite is hypertonic. If you put them in a solution with a very high concentration of solute, like concentrated brine, concentrated salt water, or sugar water, or something like that, such that the solute concentration outside of the cell is higher than the inside of the cell, water is going to go the opposite way. It's going to go across the membrane, it's going to leave the cell, and the cells are all going to shrivel up. So if we call a solution with a high solute concentration hypertonic. Isotonic would be a solution with the same solute concentration as is found inside the cell. If you place the cells into an isotonic solution, the rate of water going into the cell and out of the cell is the same. The cells don't expand or shrink, and they'll stay just steady in there like they want to be. Boiling hot dogs is a nice example of osmosis. If you're boiling hot dogs and you leave them a little too long, you might notice it'll split open like this. What can happen is these hot dogs can absorb water because the insides are very salty. It's a high solute concentration. Water can be absorbed into the hot dog, and that causes the hot dog to expand and eventually split. Same thing if you have solutions that are extremely high in solute, like honey, very high in sugar, or jams or things like that. Often we don't need to refrigerate them, and that's because most microbes, if they land on the surface, are finding themselves in a situation where osmosis is going to drain any water from inside those cells back out into the outer part with very high solute concentration, which will kill them. So they kind of have antimicrobial effects, and they, of course, I wouldn't take that too far. These things will eventually decompose. Nature will find a way. You see the same sort of phenomenon with contact lenses. Contact lenses are kind of like a semi-permeable membrane in that they can absorb water. Water can pass through to the inside of the contact lens. And while there's not really dissolved particles inside, it has sort of an effective solute concentration. And what can happen is if you put contact lenses into pure water, they will swell up and they absorb water. And the same thing, they'll shrink if you put them in a high hypertonic situation. So that's why you buy contact solution that's isotonic. It has a very specific concentration of solute, which is coincidentally equal, not coincidentally, it's by design, equal to the solute concentration of your tiers. Going back to these hypertonic, isotonic, hypotonic situation as well, if you ever go swimming in a lake and you're worried about leeches, often people will bring a salt shaker with them. And that's because if you get a leech attached to you, you can sprinkle them with salt. That makes a hypertonic solution on the outside of the leech. That will cause dehydration, which is very unpleasant for the leech, and typically they'll drop off. So what will happen? Imagine you have a situation like the one you see here, where you have a container of pure water and brine, which is salt water, attached and separated by a semi-permeable membrane. What's going to want to happen is water wants to cross the membrane to go to the more concentrated side. This will be osmosis. And that will cause the volume of the left-hand side to expand, the volume of the right-hand side to contract. What will happen, this column of water, this extra column of water, will start to exert pressure downwards, which is going to counteract the action of osmosis. So what's going to happen is osmosis will continue up to a point where this column generates a certain amount of pressure that'll stop eventually osmosis from taking place. So whatever that pressure is, we call osmotic pressure. That's the pressure required to stop osmosis. In fact, if we then took like a piston and pushed down and compressed that side, we could actually reverse osmosis to go into the opposite direction. So this osmotic pressure, this pressure that's required to stop osmosis, it's given the symbol pi, and it can be calculated for a system by this equation right here. I, again, is the Van Hoff factor. That would be the number of particles you get per formula unit of the solute. C is the concentration in molarity, not molality anymore. R is the gas constant, and that's the temperature. So the gas constant can be a number of different values, but we want to use the value of the gas constant that has the units of pressure that matches the osmotic pressure that we're eventually going to want to have. So in this case, both of these are in atmospheres. They could also both be in bar, kilopascals, whatever you like. So we have a question which says, how much glucose per liter should be used for an intravenous solution to match the 7.65 atmospheres at 37 degrees osmotic pressure of blood? So we're going to be wanting to use our osmotic pressure calculation, which is pi equals I m RT, or CRT. C is concentration in molarity. First of all, we want to look at I. Our solute here is glucose. Glucose is an organic molecule, covalently bound, doesn't dissociate in water, so I is equal to 1. The molarity, or the concentration, is what we don't know. We want to know how much glucose per liter should be used, and we can solve that in moles. We're told right away what the osmotic pressure is. It's 7.65 atmospheres. And the temperature is 37 degrees Celsius. And we would like to put that into Kelvin. So that's equal to 310.15 K. Or I guess really that's only 310 K. Those digits after the decimal are not really significant because the number we're adding here doesn't have any digits after the decimal, significant figures after the decimal. So our temperature is 310 K. And R, we want to use the units in atmospheres. So R equals 0.08206 liters atmospheres per K-mole, because our osmotic pressure is given in atmospheres, so we need to use this one. So then we just need to calculate our concentration or our molarity here. So our concentration is going to be equal to pi over IRT equals 7.65 atmospheres over 1, 0.08206 liters atmospheres per mole K, times temperature, 310 K. Temperatures will cancel, atmospheres will cancel, and you get 0.301 moles per liter. That's the concentration of glucose, that many moles of glucose in each liter to have the same ionic, not ionic strength, but sort of solute concentration, or osmotic pressure is what's often used for blood.